There are many types of wastewater, including domestic, commercial, industrial, and agricultural. Each type of wastewater has a different chemical makeup. Inadequate access to clean water and sanitation has become one of the most pervasive problems affecting human health in developing countries. Problems with water and wastewater are expected to get worse in coming decades due to increase in population and the stricter legislation regarding the environment. Mainly conventional wastewater treatment practices have been oriented to the removal of grit and floating matter, followed by the removal of suspended and dissolved organic matter. The removal of suspended matter has been achieved by sedimentation, and the bulk of the soluble organic matter is removed by biological oxidation and flocculation. These processes, when carried out in combination, have proved to be economical and effective means for removing organic matter from wastewaters. However, there are certain disadvantages associated with them. Firstly, biological process requires considerable operating control and often generates operating problems of a complex nature. The second disadvantage is that biological processes are easily upset by shock loads and require time to regain efficient operation. Besides, biological processes are unable to remove certain nutrients, heavy metals, and inorganic salts whenever there is a requirement. Although wastewater technology has improved recently, if small communities need a wastewater treatment system, these systems still need to meet current wastewater treatment requirements. In this case, the wastewater treatment systems should not only be effective and reliable, but they should also be simple and inexpensive to construct and operate. For this reason, the development of very simple and cost-effective natural wastewater treatment systems is particularly interesting. In general, natural wastewater treatment systems are divided in four broad types: terrestrial treatment methods, wastewater stabilization ponds, aquatic plant systems, and constructed systems. Terrestrial treatment methods depend on the physical, chemical, and biological reactions on and within the soil matrix. The wastewater, after a preliminary treatment step, is disposed on the soil. Technologies comprise of slow-rate, rapid infiltration, and overland flow systems, as well as combination of these types. In slow-rate and overland flow methods, vegetation constitutes a significant treatment component, while in rapid infiltration, vegetation is not necessary. Wastewater stabilization ponds are open ponds whose treatment function depends on sunlight, the microbial life, and the lower forms of plants and animals. Organic matter is decomposed naturally. With the contribution of bacteria and algae, wastewater is stabilized and its pathogens are reduced. Generally, organic content of the effluent is converted to more stable forms. Stabilization ponds include various types as sewage lagoons and oxidation, redox, maturation, facultative, anaerobic, aerobic, and aerated ponds. They can be used in a wide range of weather conditions alone, in series of various pond types, or in combination with other wastewater treatment systems. Aquatic plant systems are shallow ponds with floating or submerged aquatic plants. The most thoroughly studied systems are those which use water hyacinth or duckweed. The systems that use floating plants are distinguished by the ability of these plants to derive their carbon dioxide and oxygen needs from the atmosphere directly. The plants receive their mineral nutrients from the water. The systems that work with consists of submerged plants are distinguished by the ability of these plants to absorb oxygen, carbon dioxide, and minerals from the water column. Constructed wetlands are artificial wastewater treatment systems consisting of shallow ponds or channels which have been planted with aquatic plants and which rely upon natural microbial, biological, physical, and chemical processes to treat wastewater. They typically have impervious clay or synthetic liners and engineered structures to control the flow direction, liquid detention time, and water level. Depending on the type of system, they may or may not contain an inert porous media such as rock, gravel, or sand. Constructed wetlands have proven effective in treating municipal wastewater, agricultural wastewater and runoff, some kind of industrial wastewater, and stormwater runoff from urban, suburban, and rural areas. They are designed to exploit the various processes occurring in natural wetlands within a more controlled environment. These systems are appropriate for small communities located in rural or mountainous areas where the application of conventional wastewater systems is not economically and often technically feasible. In contrast to conventional treatment systems, natural treatment systems and constructed wetlands provide several advantages, such as the use of renewable energy sources, the absence of mechanical parts, and low construction, operation, and maintenance costs. These systems can be used to treat storm and agricultural runoff, thus minimizing their impact on environmentally sensitive areas. Therefore, these systems should be integrated into the management plans for conservation of both water and soil resources of a watershed or integrated as parts of major restoration projects. 3 are the most common constructed wetland types: free water surface systems, horizontal subsurface flow systems, and vertical flow systems. Free water systems consist of one or more vegetated shallow impermeable basins or channels filled with soil, planted native vegetation such as cattails, reeds, and/or rushes, and equipped with appropriate inlet and outlet structures. The wastewater flows at depths 10 to 30 centimeters or even 45 centimeters and is exposed to the atmosphere, the wind, and direct sunlight. Horizontal subsurface flow systems are large gravel and sand-filled channels planted with aquatic vegetation. The bed is 0.5 to 1 meter deep and is lined over an impermeable liner in order to prevent leaching. Wastewater is intended to stay beneath the surface of the porous media, flowing within the pores and around the roots and the rhizomes of the plants. The bed should be wide and shallow so that the flow path of the water is maximized. The bottom slope is normally 1%. Regarding wetland vegetation, any plant with deep, wide roots that can grow in the wet, nutrient-rich environment may be considered as appropriate for such systems. Wastewater is purified as it comes in contact with the filter media and plant roots. Vertical flow systems are filter beds planted with aquatic plants. Wastewater is introduced to the wetland surface through a network of perforated pipes in order to achieve uniform flooding. The water percolates by gravity downwards through the filter matrix. It reaches then the drainage layer, which contains a network of perforated collection and aeration tubes. The bed contains various layers of different gradation. The first layer near the bed comprises of gravel used for drainage, followed on top by layers of gravel and sand. The top layer is planted and the vegetation is allowed to develop deep, wide roots which permeate the filter media. The total depth varies from 0.90 meters to 1.2 meters. A bed slope of 1% is needed for drainage. To achieve wastewater treatment, a series of physical, chemical, and biological processes take place in constructed wetlands based on water, soil, atmosphere, and microorganism interactions. Wetland plants play a vital role in the removal of retention of organic matter, nutrients, heavy metals, and various toxic substances. The common reed, Phragmites australis, and the cattail, Typha latifolia, T. angustifolia, are good examples of marsh species that can effectively uptake pollutants and therefore are commonly used in constructed wetland. Key components of the total constructed wetland cost include the capital cost, such as the cost of land, the construction costs, such as common earth moving, excavating, backfilling, and grading, influent and effluent structures, distribution piping, liners, planting, and roads, and the engineers and contractors' fees, and the operation and maintenance costs. Constructed wetlands have a relatively large land area requirement, which is related to the hydraulic retention time and the design flow rate. Factors that affect the costs of wastewater treatment wetlands include treatment goals, wetland size, site conditions, and the need for liners. The problems related to wastewater treatment infrastructure and the environmental consequences involved are particularly important for most Black Sea countries. The Black Sea Basin Joint Operational Program 2007 through 2013 is a program under the European Neighborhood and Partnership Instrument of the European Union. This program aims to contribute to a stronger and sustainable economic and social development of the regions of the Black Sea Basin. With this aim, the program promotes projects that result in economic and social development in the border areas, gives chances for working together to address common challenges, and builds people-to-people cooperation. A Black Sea network promoting integrated natural treatment systems, Wastenet, is a network action project which aims at motivating the widest possible audience of local and regional authorities to develop and apply natural treatment systems for the wastewater treatment of rural communities. With this aim, the Wastenet project presents and promotes the widespread usage of constructed wetland technology as being an environmental-friendly, low-cost, and innovative natural treatment method.